Test- testing, testing, testing. Okay, so here we go. We're going to look at what's called measures of position for data. So we have discussed mean, median, and mode, measures of center. We discussed standard deviation and variance, which was measures of dispersion. And now we're going to be able to characterize the data with these other measures of how the data is distributed. So first I want to talk about the percentile. So if you got an 83rd percentile on the SAT, that means that essentially 83% of the people scored lower than you and 17% of the people higher. So the 83rd percentile separates the top 17% from the bottom 83%. There's a little bit of can be a little confusing. There's a lot of different kind of ideas and methods for computing percentiles. So if you look at the values 1 through 10, if you were asked, if I ask you what, the number 3 in that list is what percentile? Is it the 30th percentile, for example, because it's the third number? Well, depending on which source you look at or which method you would use, you could see one method could say it's the 20th, another would say it's the 25th, and then another would say that it's the 30th. So it's kind of hard to put an exact definition on a percentile, but roughly speaking, the pth percentile divides the lower p% of the data from the upper 100 minus p%. So we're going to look at some specific measures of position, and we have what's called a 5-number summary. And the 5-number summary is the 5 things listed here, which says it's the minimum value of the data, which is pretty straightforward. The Q1, which is the first quartile. The first quartile is basically the 25th percentile. A quarter is 25%, right? The Q2 is called the second quartile. That's roughly the 50th percentile. And Q3 is the third quartile. So therefore, that's about the 75th percentile of the data. And then the max is the biggest value. Now, for the way we're going to do it, for the second quartile, we're going to use the median, okay? That makes sense, right? The median is the value that divides the lower 50% from the upper 50%. And then to compute our first and third quartiles, we're going to use the median of the bottom half for the Q1, the first quartile, and the median of the upper half for the 75th percentile. And that'll make more sense in a minute. Another value that's not part of the 5-number summary, but it is something that we'll want to compute, is the range, which is the maximum value minus the minimum value. We also want to compute something called the interquartile range, which is the range between the third and first quartiles. Okay, that's going to be important for computing, for finding outliers. Okay, so we're going to be looking at outliers in a data set, and outliers are extreme values that essentially do not fit with the rest of the data. And there's kind of a classic standard way to identify outliers, and that's by computing these things called the upper and lower fences. And to compute the upper and lower fences, you need to know the interquartile range. Okay, so basically the way it's going to work is the upper fence is going to put an upper bound on essentially what should be a reasonable value for this data set, and the lower fence is going to put a lower bound on a reasonable value for this data set. Any data values that are above the upper fence will be considered outliers. Any values that are below the lower fence will be considered outliers as well. Okay, let's do a couple of examples. 5-number summary. Then we're going to draw what's called a box and whisker plot. Okay, so here we have some data. Let's say this is standardized test scores. The max and the min are easy to identify, okay? But what we want to do first And this is important. It's like, because part of this is finding the median, which is the second quartile. And to do that, you have to arrange the numbers in increasing order. So now I've arranged the numbers from lowest to highest. We can identify the max and the min pretty easily, right? 2400 is the max, 1100 is the min. And now, because we're defining our quartiles by using the median of the median of the lower half, and the median of the upper half, we first have to find the median of the entire data set, which is the second quartile. So the first thing you should find is the Q2, which is the median of the entire data set. And that is going to be, think about it for a second, we have 10 values, so it's going to be in between the 5th and 6th, and the median would be 1750. Okay. Now, since we've now split the data into a lower half and an upper half, we can now find Q1 and Q3. The first quartile is going to be the median of the lower half. The third quartile will be the median of the upper half. So what's the median of the lower half? Think about it for a second. It is 1500. Okay, so we're basically saying that 1500 is roughly the 25th percentile for our data set. Again, it depends on the way we're defining it is one way to do it, but that's the way that we're going to do it. Okay, that's probably one of the most popular ways to define the quartiles. Most books you look in would do it this way. The TI graphing calculator does it this way. Okay. So what's the Q3 then? It's the median of the upper half. Think about it, think about it, think about it. Yep, 2100, okay? And now the interquartile range is the difference between Q3 and Q1, which is, think about it, 600, right, okay? So for now, we're not going to worry, for this example, we're not going to worry about identifying outliers. We'll do that in the next example. But we do want to make the box and whisker plot, okay? And the way the box and whisker plot works is we're going to draw the minimum, right? So we have the box, which is the center, which is basically from the first quartile to the third quartile. And then we have the whiskers, which are the lines going out to the min and the max. So the min is 1100. The next thing you're going to put down is 1500 at the start of the box. The median, the second quartile, 1750. The third quartile, 2100, and the max, 2400. Now, it's important that you try to space these things properly. In other words, you want the scale to be right. So it's 400 from there to there. It's 250 from there to there, so it's not quite as far. Then it's 350 from the Q2 to the Q3, so it's almost the same length as this first whisker. And then it's 300 from the third quartile to the max, so not quite as far as this distance, but a little bit farther than this distance. And the reason why that's important is when you look at the box plot, it gives you a quick snapshot of how the data is distributed. So I would ask you, between which two values does the data have the highest density? In other words, if you could think about a histogram for this data, where would the frequencies be the highest? And what you will be able to hopefully see soon in practice is that would be in between 1500 and 1750. We have 25%, right, between the first quarter and the second quarter. 25% of all the data is in that 250 range, okay? So we have a high density of data living between 1500 and 1750. And that's because, does that make sense? I hope it does. Okay, that's the box plot. All right, another example. So here we're going to look for outliers. So we have the data. Here we go. Now I've ordered it from low to high, okay? So look at those numbers for a second. This is cholesterol. These are cholesterol levels for, a sample of people. one of the numbers should jump out as being funny. Think about it for a second. You know, if you have any idea about what a normal cholesterol level is, I think if you're getting up towards 300, that's pretty high. So 800 at the cholesterol level is pretty darn high, and that could mean something pretty bad. Or what is another possible explanation for that value being in our list? Think about it. Well, could have been a lab error. It also could have been a transcription error. I mean, someone wrote down these numbers, perhaps they just wrote it down wrong. So that's a suspicious number, and we can test to see if numerically it's identified as a potential outlier. So 5-number summary. We have a max and a min, right? Q1, so what's the first thing we're going to do to find the quartiles? Q1, Q2, and Q3. We're going to find the median, which is the second quartile. And the median is going to be, and that's the median of the entire data set, and that's what you want to do first, because that's going to separate your lower half and your upper half. The median is 222, that's a typo. The median is 225.5, that's right. Halfway between 222 and 229, okay? The first quartile then would be the median of the lower half. Well, now we have 6 values in the lower half, so we have to, it's going to now be the average of 180 and 180, which is 180. And now the median of the upper half, which is just 229 on, that will then be, whoops, that's the third quartile, and that is going to be 315. Now the IQR is the difference between 315 and 180. 315 minus 180 is 135, okay? And that's, again, that's Q3 minus Q1, okay? So that's the 5-number summary. You know what? I forgot to do the outliers. Let's do that now. Let me get out of this show. So we have to find the outliers. So we're going to do the upper fence, okay? And the upper fence, okay, and the formula, as from the previous slide, it's the third quartile plus 1.5 times the IQR, okay? Now, that's always the formula, so it's always 1.5, okay? So that's going to be 315 plus 1.5 times 135. I had to go run to get my calculator. So 315 plus 1.5 times 135 is 517.5, and the lower fence is going to be the first quartile minus. So basically we're looking on the right, we were looking for an upper limit for reasonable data that fit the rest of the data, which is the upper fence, and now we're going back to the left. It's essentially the, it's the same formula going the other way, if that makes sense. Q1 minus 1.5 IQR, so 180 minus 1.5 times the interquartile range. Whoops. Which is 180 minus 1.5 times 135, and that is minus 22.5. So essentially what we're looking for is, if we have any values in our data set bigger than 517.5, that doesn't fit with the rest of the data. And so that any number bigger than 517.5 is a potential outlier. Any number lower than negative 22.5 is also does not fit, and it will be considered a potential outlier as well. Okay, I mean it's possible that that number could be accurate, but it's at least a potential outlier, and it needs to be investigated. Okay. So do we have any values in our list bigger than 517.5? Yes, 800. And do we have any less than negative 22.5? No. So the 800 is considered a potential outlier. Okay. So the upper and lower fence, you got to know the IQR, and you got to know these formulas. Okay. And they're always the same. Okay. The 1.5 is always there. So it's giving us essentially, Q3 is here, right? So Q3 plus 1.5 IQR is somewhere out here. It's going to give us a upper bound that's reasonable, and then Q1 minus 1.5 times the interquartile range is going to give us a lower bound out here that's supposed to be the lower limit. Okay. And now here's a computer-generated box and whisker plot. Okay, but what you want to be able to do is, what do you do with the outliers? So the outlier was 800, and so when you make your box and whisker plot, your max and min cannot be outliers. So what I want to ask you is, what is this value here for our max on the box plot? It's going to be the highest number in our list, which is not an outlier. So the highest number below the upper fence, which it turns out to be 336. So we still have the minimum as 100. Okay. We still have the Q1 as 180. We still have the median, the Q2, as 222.5, or 225.5, sorry. The Q3 is still drawn at 315, the third quartile. And the max, though, now is going to be 336. And then the 800 is marked out here as a special value, which indicates that that is a potential outlier. And you can use a dot, you can use an asterisk, it depends. Any of those things are okay. All right? Same thing goes for if we would have had a value, if we would have had an outlier on the low end, then we would have done the same thing. The outlier, you can't have more than one. You can have multiple outliers. They would have been marked over here with a dot. And then the minimum on the box and whisker plot would have been the smallest data value, which is still higher than the lower fence. Okay? So that's a box and whisker plot with outliers. Okay? Or with one outlier in this case. Okay? Now what we're going to do next is we're going to say, okay, well, can you look at this data and kind of get an idea of how it's distributed? Where is there, kind of high density? There's here what I've done is I've shown the box plot kind of superimposed or, above the what's called a density plot. A density plot is essentially, if you kind of think of it as a histogram, which shows kind of the relative frequency of, data between 180 and 222. There's 25% of all the data would come from that 40 interval. So we have a high density spike kind of in that area. Okay, so I hope that you can kind of get a feel for how to relate the box plot to the density plot. Okay. So let's practice. So what I've done, here's a box and whisker plot, and I want you to try to look over here. Here are some density plots. So which data distribution, so this is essentially a data distribution, and what you want to think about it is if you had all the data and you did a histogram, where would you have high frequencies and where would you have lower frequencies for a specific interval. Okay, so what do you see? If you had to put a shape to this data, which one is it? Or maybe you can rule some out. So this would be a symmetric distribution. This would have high density on the right, And I think we can rule those out. So we have a higher density right here, right? And that's on the left. And over here, it takes all of this range for us to have this upper 25%. So I think we can narrow it down between A and B. So for now, we're going to pick, it's either A or B, okay? And I hope that makes sense. We'll come back to that in a minute. There's one that's A and there's one that's B, and we'll see the difference. Okay, so what about this one? So can we rule any out? I mean, first of all, what I hope you can see is that this would be a symmetric data, okay? Now, the next thing would be, is it, so how many symmetric distributions do we see in our choices? Well, we see C is symmetric. E is also symmetric. This is called uniform. This would be where the data is completely evenly distributed. And then F is also symmetric. So, if we could pick between C, E, and F, can we rule one out? Well, if you notice, the distance from the minimum to the first quartile is not the same as the distance from the first quartile to the median. And so what you see is we have a density, high density basically in the middle, between the first quartile and the third quartile. These spacings are smaller than the spacings for the lower 25% and the upper 25%. So we're going to have a density spike somewhere near the middle. So we can now narrow it down to C or F, and we'll be able to decide in a minute which is which. I hope that makes sense. Okay, so basically this is the similar plot. We still have, it looks like this distance in the lower 25% is still bigger than the distance between, say, Q1 and Q2. So we're going to still have a little bit of a density spike, if you will, in the middle. But, is it as high as the one here? Here we have a higher concentration in the middle. Here we have still a little bit less. So, one of these is C and one of these is F. So this one, what do you think? This one is going to be C, and this one is going to be F. Higher density in the middle for C than for F. Now what about this one? What do you think? So think about this boxing whisker plot would go with which density plot? Good, I know you all picked D. And what about this one? So we had one, if you remember, that was here, and now we have this one. So those two are going to be A and B. So this one is going to be which one? That's going to be A, and this one's going to be B. So I hope you could see why, the difference. This one we have a, very density, 50% of the data is in this small interval, right? So we're going to have a higher density over that small interval. Okay, so this would be B. And this one is the tricky one. But if you notice, all of these distances between the min and the first quartile and second quartile and third quartile to max, those are all the same. So that ends up being distribution E, which is called a uniform distribution. Okay. And then let's just go through. So what is A and B are called what in terms of distribution? So you have uniform, symmetric, left skewed, right skewed. So A and B are what again? I think we've discussed this. A and B are right skewed, and where it goes with the tail. C, E, and F actually are all symmetric, right? Basically, you have the same density on the left and the right of the median. D is what? D is left skewed, and E is uniform. Okay, so be able to do that. So what I hope you could do is now just look at the box plot and tell me, that is going to be right skewed data just from the box plot. That's going to be symmetric data. Okay, that's going to be symmetric data just from the box and whisker plot. That's going to be left skewed data. That's going to be right skewed data. That's going to be symmetric data also, and uniform. Okay, so just from the box plot, you can get the skewness or the symmetry of the data. Okay, so be able to do that.